In this video, I have discussed questions on CRO, and these are structured questions. First question is from 9702, that is AS level 21, variant 21, October November 2013. This is question number 2 of that year, and the details are there. A source of radio waves sends a pulse towards a reflector. The pulse returns from the reflector and is detected at the same point as the source. The emitted and reflected pulses are recorded on cathode-ray oscilloscope CRO as shown in figure. So the appearance of the trace is shown in the figure. The pulse with longer amplitude is transmitted pulse, and pulse with shorter amplitude is reflected pulse. CRO shows the transmitted and reflected pulse. The time-based setting, that is 1 centimeter, represents here 0.2 microsecond. And again, I will make you recall that the time base is along x-axis. Okay, so that is the horizontal sweeping of the beam along x-axis. So time is taken along x-axis. So setting is 0.2 microsecond per centimeter. Radio waves, they travel at a speed of light. We have to find out the distance between the source and the reflector. Here I will first give you some pictorial view of the question. That is, there will be a source of microwave and there will be a reflector. This is source and this is reflector. Sound waves, radio waves, they travel towards the source and reflect. So this distance is d. So the total distance is 2d. Is 2d. And time taken to travel that distance is what? We have to count the number of squares or blocks between transmitted and reflected pulse. So 1, 2, 3, 4. And speed of radio wave, we know that they travel at a speed of light. And why the reflected pulse have lower amplitude? Of course, because of the absorption, loss of energy, and some energy is absorbed by the reflector as well. So reflected pulse has lower amplitude. So V, the speed of my radio wave is 3 into 10 raised to the power 8 meter per second. So which formula we will apply to calculate the distance? V is equal to distance over time. So distance is 2d because d is from source to reflector and plus d is from reflector back to source over time. So V is 3 into 10 raised to the power 8 is equal to 2d over t. What we will write for t, the time which reflected pulse takes, that will be setting multiplied by 4. So setting is 0.2 and there are 4 blocks. So it means 0.8 microsecond. Okay, so 0.8. So what will be D? 3 into 10 to the power 8 multiply by 0.8 divided by 2. If we make D subject, we get this. Okay, so let me solve to find out the distance between source and reflector. The answer is so 0.8. I have to use this as well, microsecond minus 6 into 10 raised to the power minus 6. So answer is 120. The distance between the source and the reflector is 120 meter. So here the distance 120 meters. Now determine the time-based settings required to produce the same separation of the pulses on CRO when sound waves are used instead of radio waves. The speed of sound waves is 300 meter per second. So we have to get the same separation between the transmitted and reflected pulse, and the setup is also same. D is 120 meters, same distance. So we can solve it in different ways. That is the distance is 120 and the time is 0.8 microseconds. So time is 0.8 microseconds. Since the sound waves are slower, what is the speed of sound waves? 3 into 10 raised to the power 2, or you can say 300 meter per second. And of course, they are 10 raised to the power 6 times slower than light. So we again should have 4 blocks between the transmitted and reflected pulse. So what should be the setting? One square, there are 4 blocks. Means first we should, and distance is same, that is 120 meter. First we should find out how long will sound waves take. Of course, they will take 10 raised to the power 6 times longer time. Okay, and we can calculate also using the same formula, V equal to 2D over T. So 300 equals to 2 into 120. This is now known to us. Same separation, same setup, and the time is to be calculated. So this is T equals to 240 over 300. What will be the total time? taken by sound wave to return. That is 0.8 seconds. 10 to the power 6 times longer time. And what radio waves were taking? 0.8 microseconds. Micro means 10 to the power 6 minus 6. So they are taking 10 to the power 6 times greater time in order to travel from the source to reflector. So the setting will change accordingly. So the time interval, there should be 4 blocks between this uh, transmitted and reflected pulse. There are 4 blocks. Okay, so what will be total time is 0.8. 0.8 seconds. So what should be the, and time based setting is time for one block. So what will be the time for one block? We will divide this by 4 because there should be the same separation between the transmitted and reflected pulse, and there are 4 blocks. So each block will be 0.8 divided by 4 means 0.2 seconds per centimeter, or zero point 0.2 seconds centimeter minus 1. So this is the answer. The setting is this, and the answer is 0.2. The next question, this is based on again the CRO and almost the similar type question, 9702 AS level, variant 21, October November 2015. The signal from a microwave detector is recorded on a cathode ray oscilloscope, CRO, as shown in figure. So this is also the question number 2 of that year. So here 5 small squares are equal to 1 centimeter. So one wave, the time base setting is 50 picosecond per centimeter. So we have to determine the wavelength. Okay, so we should see there are 5 blocks, and each block, five small squares, 1 centimeter. Still here, this is 1 centimeter. So when we count 5 centimeters here, so what is the total time? This is 1 centimeter. So total separation is 4 centimeter. The, so this is 4 centimeter. 1 centimeter is equal to 50 picoseconds. Setting is 50 into 10 raised to the power minus 12 seconds centimeter minus 1. So time of one wave. One wave is here, from here to this. So what is the time of one wave? That is the time period. So we will multiply the setting with number of centimeters. So how many centimeters are there? 1, 2, 3, and 4 centimeter. So 50 into 10 to the power minus 12 into 4. So when we solve this, what will be the answer? 50 exponent minus 12 into 4. 2 into 10 to the power minus 10. I will solve it little at the appropriate place. that is here. So time period is 50 into 10 raised to the power minus 12 seconds, and setting is this is second, not time period, this is setting. So this is the way. Seconds centimeter minus 1 multiply by 4, because there are 4 centimeters for one complete wave. So 4 centimeter. So centimeter and this get cancelled. So time is 2 into 10 raised to the power minus 10 seconds. What is wavelength? The famous formula V equals to F lambda. So lambda equals to V over F. So 2 into 10 to the power minus 10. So frequency is 1 over F, 1 over T. F is equal to 1 over T. So when we take the reciprocal, the answer is 5 gigahertz. 5 into 10 raised to the power 9 hertz. So V is equal to 3 into 10 raised to the power, because microwaves, electromagnetic waves, so they travel at speed of light, 3 into 10 raised to the power 8 meter per second, and frequency 5 into 10 raised to the power 9. So answer is 0.06 meters. 0.06 meter. So this is the wavelength of the microwave. Now let us solve the next part of the question. Wavelength is 0.06. And now the second part, the signal from a radio wave detector is recorded on the same CRO. Now the waves are, the source is changed. First in part had a microwave and now the radio waves. So the wavelength is longer, that is 1.5 into 10 to the power 3 meters. Determine the time base setting required to display the same number of oscillation on CRO as shown. Excuse me. So 1.5 into 10 to the power 3 lambda. You have to calculate the frequency of radio waves. F is equal to V over lambda. 3 into 10. Radio waves also travel at the same speed. So 3 into 10 raised to the power 8 divided by 1500. The frequency is 200,000 hertz. So what will be the time period? T is equal to 1 upon F. After finding out the time period, we can calculate the setting. So what is 5 microseconds? 5 into 10 raised to the power minus 6 second. So what should be the setting? We should have the 20 blocks. That is 20 is 4 centimeter. That means each 5 centimeter is each 5 block is 1 centimeter. So there are 20 blocks means 4 centimeter. So this is there are 4 centimeters in between. Okay, so we have to get the same pattern of the wave on the CRO for radio waves as well. Okay, so the microwaves were occupying 4 centimeter and the same should be occupied by radio waves. So but the time period was different. Here the time period is 5 into 10 to the power minus 6 second. So we should know the time period is equal to total time over number of waves. One wave occupies 4 centimeter. Five into 10 raised to the power minus 6 equal to total time. Total time means number of centimeters into setting. Setting into number of centimeters divided by wave. So this is only one wave which is occupying 4 centimeter. So what will be the setting? We will have setting equal to this is 4. When this 4 goes down, goes to the other side, it will be dividing 5 into 10 raised to the power minus 6 divided by 4. So answer will be 1.25 microseconds per centimeter. 1.25, sorry, 54 minus 6 divided by 4. 1.525 and this is microsecond. 5 divided by 4 is 1.25 and this is 10 to the power minus 6 means micro second per centimeter. So how will we express our answers? Time-based setting 1.525 if you express it in two significant figures. So you may write 1.3 and unit microsecond, centimeter, -1. So that's all. Till next video. Allah Hafiz.